Welcome back to our discussion on detection of data problems. In the three categories that we have discussed, the three categories include problems due to nans and nulls, problems due to noise in the data that affect data integrity, and problems due to storage of the data because we have to decide what data type the data is. And sometimes we decide wrongly. Sometimes the library code decides wrongly, and so on and so forth. And because of that, we will end up facing a lot of issues as we have discussed in the classroom in the slide setting. But right now, let's get to our spider experiment lab. So please run your spider and let's begin our experiment by defining our famous df3 here, right? And I need numpy and pandas. And then we will be able to derive from df3 our df7, df3. So we see, I need an F here. So we see that df3 indeed was extracted with the numbers. Now notice that the original df3 had integers, right? But now our content filtered df7 are storing the correct values, but in basically it's quite obvious, it is floating point because nans are associated with floating point type. So in other words, the source data was promoted from int type to float type in order for nan to proceed to be possibly stored. If there is no nan, then the right data type should be at int level. Okay, so here we see this very secret and mysterious auto conversion to float. Why? Because in int, the int type cannot store a nan. So for nan to happen, you have to have a float type. Then what happens? So now we are able to, we would like to drop, right? Drop NA. And we'll see how we can drop. So we have dropped all the rows having nan. that means all the rows basically, because there are only two rows, and both rows have at least one nan. Then we try to have the columns dropped. So any column with at least one nan is being dropped. So what happens then? So this is the first one. The second one is that columns A, C, and D are all having at least one nans. So we are left with only column B. Column B. Now, what else? We can also run the drop NA with the in place equals to true. Okay, so we can do that. And we get df7 being reduced to down to just one column. Okay, and this is the df7. This is the final version that we will process on because we wouldn't risk disturbing the statistical outcomes with nan values. Okay, now next we talked about the data problems coming from noise. So let's create some noisy data frame, which is what we have seen, the John, Mark, and Gwen data frame. We can adjust it a little bit here. Okay, so we have this, and notice that I have inserted the spaces before and after John, before Mark, and after Gwen, but with two spaces. So when we print this out, we get this. So it's quite obvious that there are some spaces here, right? Yeah, but in when you have a lot of data, it is not possible to detect such spaces. Like here, there are spaces after Gwen being stored, and we have no idea whether this is actually just spacing to make it look neat or actual spaces stored in Gwen. So we cannot trust what we see on the screen. Um, so what we do is that we have to run some sort of a filter to make sure that every element has been inspected, right? At least all the, if we are worried about values, noise, like these that are slightly off zero. So every single element that is supposed to be inspected has been inspected. So whenever it is a bit less than the threshold, that means it's just slight disturbance, then we say, okay, most likely it's measurement noise. We will just, reset it to zero, hard reset it to zero. Okay, so this is important to ensure that we don't magnify the noise. Next, we also talked about using apply map to inspect and round off noise in the case of creeping into the third decimal place, fourth decimal place. And in this case, we are saying that no, we like to round to zero, no decimal place. Okay, so how do we do that? Well, apply map. Okay, for all the cells that are basically, what do we have? Non-string, right? Non-string. Okay, so what if we want to round to one decimal place? Just change to one, and we get one decimal place. Okay, so let's go back to zero. Okay, good. Now, so this is about noise creeping into decimal places. Then we also have noise in storage, which are strings. So now we are going to apply the .str.strip function, which basically takes a string and removes any prefixing and suffixing spaces. We do that only for the case when the column data type. So the way to access the column data type is this: pandas pd.api.types.is numeric. Why do we use is numeric? Because we don't want to go through all the many different numpy numeric types, because there are many different types like int 32, int 64, float 64, decimal, I think, and so on. So there are too many of them. And if you miss out any one of them, and should that column be somehow, whether it's accidentally or purposefully, set to that kind of numpy supported numeric type, and it's not in this list here, then you're gone, right? Fortunately for pandas, we are able to tap on it because pandas works very closely with numpy, so it can check just by using this that no matter what numpy has, various kinds of numerical data types, so long as it's numerical, it will be true, and that is exactly what we want. So if it is false, then we know that it is not numerical, then we assume, all right, it is string. That's quite safe. All right, and we will basically then perform a string.strip of the spaces in front and behind. But if it is any form of numeric type, then we return itself, the whole column vector. And then we perform the apply without axis equals to whatever. So there we go. We have done that. And now John, Mark, and Gwen are properly aligned. All right, quite safe to say now, at least visually quite convincing, but we never know. Don't trust our eyes. Okay, um, let's see what else we've got here. The next category, yes. So the next category is about, what do we have? The next category is about the data type. So first we revise what is our df8 underscore 0, and we check, all right, what is the data type. I put a SS in front because we know that it's going to be one type per column, and the way pandas returns that information is in a series. So that's why I use the SS. Whenever you see by now you should notice that whenever I put an SS, is to remind myself that the data value will be potentially a series. But using a variable name SS doesn't mean, all right, I mean, I could have made a bug or program mistake somewhere that an int gets stored into SS8 underscore types. So we're just using the variable name to reinforce my own programmatic thinking that I'm expecting a series, right? So that when bugs come out and I print SS8 underscore types and I don't see a series, I'll be like wondering, why am I seeing an int when I was expecting a series? This is one of those programming tricks that we ensure we have in ourselves self-consistency. Okay, so let's run this and see. Correctly, A is a kind of object. Now, I agree with you. You probably feel a bit disappointed, right? Why isn't it showing string? It would have been nice. And I can share that sentiment. Um, but this is the best pandas goes. It says A is an object, remember, because each column, all the cells must have the same type. So object is the most generic. Then we have float 64, 64, 64, and for BCD. Next is we ask, is the data type of B a float, specifically a float 64? So here, this statement could look little bit I don't know, annoying or disturbing, but actually not difficult because assignment has to be computed first, right? It makes no sense to say let's assign the data type of B into Dan's the answer variable and then check whether it's equivalent, check what, because assignment has no return value, right? So it wouldn't make sense. And the right way to think about it is can only be like this. If you are sort of worried about confusion, you can always put a bracket here. There's no harm, and it will make it clear that we should check is it going to be a true or false and put it inside answer.